Okay, good afternoon, everyone. Hope everything is going well for you all. And we have another lecture via Zoom for MENG 260 class. Today is June 10th. We're almost getting to the end of this week, and then we have one more week left to finish this course. I have graded you, I think everybody's exam so far, okay? Everybody has done really well, and nobody failed, and some of you did really, really well, and I was so pleased that you guys knew what to do. So that was exam on chapter 2, 3, and 4, and then the exam number 2, midterm exam number 2 will be on Monday, which covers, chapter 5, 6, and entropy, chapter maybe mixture of 7 and 12, because chapter 7, it's a overview of second law of thermodynamics, goes into more details of how to calculate the entropy for ideal gas and non-ideal gas. Okay, so chapter 5, it was the topic of energy balance, mass flow rate, and the unit, as I mentioned yesterday, it has to be balanced, consistent. So please pay attention to that, and you will be able to do well on the second exam. The second exam is going to cover the topics of thermodynamics devices, such as turbine, compressor, pump, heat exchangers, and possibly throttling devices, okay? And we will be dealing with the nozzles and diffusers. Okay, and just review the lecture notes and make sure you get a good grasp of the formula and assumptions. You have to make assumptions. And I think if you work on homework that they have put together, those problems will really give you the insight of what chapter 5 and chapter 6 is all about, okay? Let's try to do those problems, and it will really, really put you in a good position because it reviews everything for you. So, any questions before I start the lecture? No, okay? But if you have any questions after the lecture, please hang in there and I can go over any questions you have. All right, so let's go. So we have already discussed about the heat engine, thermal efficiency of heat engines, pump, refrigeration cycles, and air conditioning, okay? And then we're gonna go into maybe more of Carnot cycles, which is considered to be a reversible cycle, and comparing the reversible cycles with non-reversible cycles. So heat engine is a devices that convert heat to work. That's good, okay? Heat to work. They receive heat from high temperature source, like solar energy, oil furnace, nuclear reactor. And then they convert part of this heat to work, usually in the forms of rotating shaft. If the shaft is not rotating, then no work is done, okay? They reject the remaining waste heat to a low temperature, we call it sink, okay? So the work net output, the energy coming from the hot source or hot environment at high temperature, and then that amount of heat, we call it input energy, and then it goes into the heat engine, and then the work out and Q out, the portion of it goes into low temperature sink. Okay, heat engine and other cyclic devices usually involves a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called a working fluid. Okay? Part of the heat received by a heat engine is converted to work, while the rest is rejected to sink. Okay? This is an example of paddle wheel, or we call it a propeller. So when it's spinning, then we have the work, and then the energy will be generated. Okay, so work can always be converted to heat directly and completely by the reverse. But the reverse is not true. You cannot have the hot surface and expecting that hot surface to increase its temperature naturally, which is not possible. And here we have a beautiful picture of a steam power plant. Again, if you're planning to go into higher level courses in thermal sciences, you will be designing a system, whether it's an open system or closed system, and that will really help you to, if you wanted to maybe concentrate in the area of thermal sciences, this is the route to go, okay? This is the approach. A lot of people as mechanical engineers maybe have emphasis on thermal sciences than the majors in this area, okay? So, and a steam power plant, the net work out is the difference between the work out minus the work in, okay? Or the work of the cycle that we used to call in heat engine. So, and W net out could be written as Qn minus Q out, okay? In terms of energy transfer or as a heat. So Qn is amount of heat supplied to steam in boiler from a high temperature source, okay, furnace. So that is the boiler, the heat goes into that, and Q out, the amount of heat rejected from steam in condenser to a low temperature sink to the river or atmosphere, okay, to outside, to the surrounding. And work out is the amount of work delivered by steam as it expands in turbine, okay. And that's a turbine, and we have the work in, amount of work required to compress water to boiler pressure, okay. So this is the complete cycle of a steam power plant. And you must have the condenser. If the condenser is not there, we call it the open system, which is not a good idea, okay. It doesn't have any value. So we need to have a condenser to remove the excesses water vapors, because the water vapors is going to damage the pump that is going to then send it to the boiler, and then the temperature will increase, and then it goes into the turbine, and turbine is going to do mechanical work and is going to run it generators or and mechanical work. All right, so and then we have thermal efficiency. Okay, we have already discussed this. This is just a review. So for heat engine, the thermal efficiency is work net out, the net amount of work leaving the heat engine divided by amount of energy, Qn, or we call it QH, okay? QH is a Qn in here. The label, okay, do not get confused. That's the temperature of hot reservoir, and Qn to the heat engine, and Q leaving the heat engine, we call it the lower heat, or QL. So a schematic of the heat engine is given in here, and the thermal efficiency is, because we know that the Qn minus Q out divided by Qn, because that's the W net out. If you divide this fraction by Qn, so Qn divided by Qn is 1, and then Q out over Qn, all right? So this will give us the Q out cannot be larger or cannot be 0, okay? So if we have a 0, 0 over number is 0, and we cannot have a thermal efficiency that's 100%. So Q out must be smaller than Qn, and then when you divide that, we get a number less than unity, and you get 1 minus that gives us a thermal efficiency, okay? Which is the thermal efficiency is less than 1. So if we are in terms of W net out, or QH minus QL. That's the thermal efficiency again. And then you have the QL over Q out in this situation here. Okay, so the definition of thermal efficiency is always the network output, okay, and what we want, what we put into the system, okay? We have to put energy into the system. That means it costs money, what we wanted to get out of this system or cycle, okay? Okay, and we save Q out in a steam power plant. Let me see if okay. Every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized condition, okay? In a steam power plant, the condenser is the device where large quantities of waste heat is rejected to rivers or lakes or to the atmosphere. Can we not just take the condenser out of the plant and save all that waste energy? This will be a question. Can we just take the condenser out of the power plant and save all the waste energy? The answer is unfortunately no, okay? For the simple reason that without a heat rejection process in a condenser, the cycle cannot be completed, okay? So that's why. All right, so we go to the next one, which is the second law of thermodynamics. They call it the Kelvin or Planck statement. It is impossible for any devices that operate on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, so you need to have two reservoirs. Okay, all right, so that's what they're trying to say here. No heat engine can have a thermal efficiency of 100%. So we talk about that. No heat engine can have a thermal efficiency of 100%, or as far as for a power plant to operate. The working fluid must exchange heat with the environment as well as the furnace. All right, so that is the definition of heat engines and thermal efficiency. Again, they're just showing another schematics of that. This is the same thing here. All right, so let's see. These are the refrigerators. This is the heat pump. Okay, this is the heat engine. That's a heat pump, and that's a refrigerator. Okay, those are the three different cycles. Schematic of heat engine, we already went over this. And then for heat engine or heat pump, okay, here is for heat engine, the work out. Here, the work is going for heat pump. The work is going into the system by means of like a mechanical work or piston and cylinder here. And then the heat is going to go into this heat pump from the low reservoir, and then the amount of heat transferred to the to heat the space. We're going to talk about the heat pump because that's in some cold environment, they use heat pump because of the cost of electricity, okay? Because they wanted to minimize the amount of energy that is going to use to warm the environment, the house or the building. So they use heat pump. And refrigeration cycle, everybody has the knowledge of, refrigeration cycle. And we're going to talk about the fluid that is used in a refrigeration cycle. They call it the Freon or R12, okay, which is not really, it's against the law to purchase the R12. But anyway, so the objective of heat pump is to supply heat into the warmer space. And the objective of a refrigerator is to remove heat from the low temperature from the cool space. So those are the three cycles. So refrigerators and the heat pump. The transfer of heat from a low temperature medium to a high temperature one required a special device is called refrigerators. So the transfer of heat from a low temperature medium to a high temperature one required a special device called refrigerator. Refrigerators, like heat engines, are cyclic devices. The working fluid used in the refrigerator cycle is called the refrigerant. or Freon, or we call it the R12. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle. In a household, refrigerator is the freezer compartment where heat is absorbed by the refrigerant, serves as the evaporators. Okay, so we have in this refrigeration cycle, we have evaporators, condenser, and then the compressor and expansion valves. Okay, and that's the refrigerated space. So the evaporator and the coil is used behind it. Okay, so for the evaporators, and we have a coil around it. And refrigerator where the heat is dissipated to the kitchen, air served as the condenser. So this is the schematic of refrigeration system and typical operating conditions. Again, if we wanted to learn about design of HVAC, heating, ventilation, and air conditioning, and designing a refrigeration cycle, you need to take another course, the upper division course in thermal sciences, which I think Dr. Jacobitz mentioned that this is just a fundamental, this is an introduction to thermal sciences for students to become familiar with the terminology and the language of thermodynamics, fluid mechanics, and heat transfer. And then you can take some upper division courses that will get involved into designing this type of systems, okay? And also you do the project. Because I wanted to give you a project since we're doing this online, it's not possible to work in a team and not everybody's in San Diego. So since you're all over the place, it was not a good idea to just ask you to do the teamwork or collaborate with each other and work on a project, which I normally do that for properties of materials class or engineering materials class. They have a team project. Anyway, then we go to coefficient of performance. Okay, we have thermal efficiency and we have coefficient of performance. The efficiency of refrigerators is expressed in terms of coefficient of performance. So remember that the efficiency of a refrigerator is expressed in terms of the COP. The objective of refrigerator is to remove heat, okay, from the refrigerated space. Okay, that's what we want. And so coefficient of performance of R means refrigerator, it's desired output divided by required input. So work input into the refrigeration cycle, and then the desired output, which is the removing the heat from the refrigeration cycle. So desired output, which is a QL, and required input, W net work, which is for input, okay, input into the cycle. All right, so that is the formula, which most of you did, or all of you did really well on the last problem on the homework that asked you to find the thermal efficiency. And I think 100% everybody got it right. And you had a good ideas of how to use tables. And those tables are a little bit, tricky because you have to watch whether you're looking at the air or ideal gases or other, monoatomic gases or diatomic gases. And if you miss that, suddenly you're, like I have made that mistake because I was not watching, the top of the table. And I thought that was, for example, is a saturated water vapor table, but it was not, it was incorrect. I wasn't refrigeration table. So just, I think you guys have better eyes so than I do, because age is gonna cause problem with the eyesight. So, and I don't wear glasses because I'm nearsighted, so it's causing problems for me. But anyway, guys, please review all this, the coefficient of performance, and for the heat pump, the same way, okay, coefficient of performance of the heat pump. And it says the coefficients coefficient of performance of a heat pump is equals to also coefficient of performance of R, refrigerator, plus 1. Remember that coefficient of performance is not the same as thermal efficiency, because thermal efficiency is less than 100%, and coefficient of performance could be 2, 3, 4, 5. It's more than 1. Okay. So the objective of heat pump is to supply heat into the warmer space. We already talked about that. Okay. And let's see what this is saying. Okay, this is the heat pump. Okay, most heat pumps in operation today have a seasonally average coefficient performance of 2 to 3. Okay, because you have to, when you purchase thermodynamic devices, or when you purchase, the heat pump, AC, and all that, it costs money. So sometimes you don't need to have a high level of heat pumps or AC. For refrigerators, you just have no other choice, because all refrigerators are almost the same, but it depends on the model of the refrigerators, okay? And then the amount of energy is going to use to cool the compartment of the refrigerator, so you have to pay. And AC is costly also to design an air conditioning unit, or we call it refrigeration, or another name, we call it AC, or air conditioning unit. And if you spend money on getting a 2 to 3 tons of refrigeration cycle or AC, and is not needed, that means you're wasting money and energy that is not needed. So it's not a comfortable environment if you have too much cold air coming in. So that's why the mechanical engineers design a HVAC based on the environment that you are designing for the residential building, based on the square footage, for commercial building, again, based on many factors, okay, many factors. And if someone is interested, maybe you can just, work in an area of people that they do design of air conditioning and heat pump, and you will learn so much about how, how these things will be designed. And in the old time, we used to sit down and do the calculations by hand. It took me, for example, a week to find the overall heat transfer coefficient and to determine the size of the AC that needed for this house that they gave me the project. They said, you need to come up with the tons of refrigeration, what is a 1.5 ton, 2 tons, 3 tons, 4 tons, and it is directly proportional to the money that you pay when you have a higher size of AC. And in terms of horsepower also. So most existing, and I worked on that, and because when you're rookies and you wanted to just do these things correctly, and you follow the guidelines of thermal sciences, and you have to calculate everything to make sure that you have a correct design. So, but the people that are experienced, they tell you that you didn't have to really go through all this, work. Based on experience, they could tell you, just to say, give me the size of the house, I'll tell you that this is the size you need for AC. And I said, I spent a week trying to figure out how to design it. I said, you're a rookie, that's why. When you're a rookie, you got to just learn from scratch. And then after many years of experience, you don't have to do all that. And nowadays, there's a computer software available for those, and you can just input information, and it tells you what size of refrigeration you need. Okay, all right, so most existing heat pumps uses the cold outside air as the heat source and winters, okay? And cold climates, their efficiency drops considerably when temperatures are below the freezing point. In such cases, they use geothermal or ground source heat pump that uses the ground as the heat source can be used. Such heat pumps are more expensive to install, but they are also more efficient. Air conditioners are basically refrigerators. That's why I'm talking about the refrigeration here, the tons of refrigeration. So basically, the refrigerators whose refrigerated space is a room, and instead of being a compartment that you put your food in there. So, or a building instead of food compartment. The COP of refrigerator decreases with decreasing refrigeration temperature. Okay. Therefore, it is not economical to refrigerate to a lower temperature than needed because of the money, the cost involved. So, in case, again, one day, I mean, we all need an AC in our house because especially if you live in Middle East and you cannot live without AC. 24 hours the AC is on. So it's otherwise the life is so uncomfortable. But I don't know how the people live back in maybe 50 years ago, 100 years ago. How do they survive in that hot environment? Okay, so anyway, energy efficiency rating, EER also, the amount of heat removed from the cooled space in BTU for 1 watt hour. Okay, this is it comes to the cost, okay, cost of amount of electricity consumed. So EER, the energy efficiency rating, is by definition, when you have it 3 lines, means by definition, it's approximately 3.412 times the coefficient of performance of that refrigeration cycle. Okay? So that's how you can calculate to see how much you have to spend per day, per month, per year to cool the space. Okay. All right, so I leave it up to you to do more research on that. Okay, all right, great. This is the second law of thermodynamics. We have already talked about this, okay? It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature. It states that, the second law of thermodynamics, it states that a refrigerator cannot operate unless its compressor is driven by external power source, such as an electric motor, right? So that's where we pay, okay? Anyway, so a refrigerator that violates the Gaussian statement of the second law. Yeah, so we just wanted to understand the language of coefficient of performance, thermal efficiency for these cycles. And again, this is the perpetual motion machine that violates the first law of thermodynamics. So what does then perpetual? Because you have a device and without any external push or work, it doesn't really, it might just, because of the frictions and all other factors, it will not really perform. So that is called a perpetual motion machine. And if it's a PMM1, perpetual machine or motion machine, any device that violates the first law or second law of thermodynamics, a device that violates the first law by creating energy is called a PMM1. A device that violates the second law is called a PMM2. Okay, this is the. I don't know whether you had a chance to watch this in YouTube. Let me see if I can maybe just finish this and show you the video. It's really fascinating video about the PMM1 and PMM2, perpetual machines that violate the second law of thermodynamics. Okay, all right, so. And then we have a reversible and irreversible processes. Reversible process, a process that can be reversed without leaving any trace, okay, on the surroundings. So a reversible process, make sure that, we want to make sure that the system comes back to its original position. And a process that is not reversible, all the processes occurring in nature are irreversible. Okay? So why are we interested in reversible process? First, they are easy to analyze. They serve as an idealized model or theoretical limits. Okay, let me see. Okay, theoretical limit to which actual processes can be compared. Like Carnot cycles, it's 100% reversible cycles. Okay, Carnot cycle. Reversible processes deliver the most and consume the least work. Okay, reversible process. So if you have a piston and cylinder and you compress a sample of air at a higher speed and then you let that come back to its original position, that's an example of reversible process. Or PDV work, we call it PV work. Okay. So, and a frictionless pendulum. So it goes up and then comes back to original position. So um, that is the motion of this pendulum can be calculated in dynamics course, okay, dynamics. And then you need to calculate the mass moment of inertia of this device or pendulum, okay. So this, they're trying to show you that if you have a soda and you leave it on the counter, if it's already cold, you brought it, you took it out from the refrigerator, and then you can see that it doesn't really get cold, cooler. It's going to get warmer because it has to have an equilibrium with an environment. Okay, so here we have the factor that cause the processes to be irreversible are called irreversibilities. They include friction, restrains expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solids, and chemical reaction, which we use that in materials class. We have a sample of aluminum or carbon steel or any other type of materials. Uh, I like to do the test on ductile materials because you can see that the materials is going to stretch without, and it doesn't snap right away. So when you apply the load, the tensile load. And if you remove the load up to the certain point, we call it a yield point, then the materials will return to its original positions. So that's a reversible process. No harms done on the materials. The materials stay the same. And but if you increase the load and the materials is going to uh, uh, go from elastic region to plastic regions, eventually it reaches the ultimate tensile strength and then it will fracture. And then you can study the fracture of that sample. And there is a topic in fracture mechanics that goes into details of how the materials fails or the failure analysis. Okay. Again, this is just trying to show you that, okay? All right, so internally and an externally reversible process, internally reversible process, if no irreversibility occurs within the boundaries of the system during the process, and then externally reversible if no irreversibility occur outside the system boundaries, okay? And then we have totally reversible process. It involves no irreversibility within the system or its surrounding, and so on. So we can you can look at these samples here, all right? So then I wanted to, I was waiting to get to this slide here. Probably the best known reversible cycle is the Carnot cycle, okay? Carnot was a French engineer, and he always claimed that his cycle engine is the most efficient one. It has a higher thermal efficiency. The theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. That's good to know, okay? The background, the knowledge, and the environment of thermal sciences. When you have a cycle, they call it Carnot cycle, is composed of 4 reversible processes, 2 isothermal and 2 adiabatic. And it can be executed either in a closed or a steady flow systems. Okay? So we have state 1 to state 2, the amount of heat transfer into the cycle, and that at isothermal or constant temperature, isothermal process. And then from 2 to 3, that's the adiabatics, no heat transfer in and out of the system. And then the temperature is constant. And then we have 3 to 4 is also isothermal, okay? And we have 4 to 1 back to a state 1, we call it the adiabatic process. So reversible isothermal expansion, process 1 to 2, constant temperature, reversible adiabatic expansion, process 2 to 3. Drops, okay, temperature drop from high temperature to low temperature. And you guys are really knowledgeable right now. By now, I can see that you can, sketch the diagram, PV diagram, TV diagram, and so on, okay? So reversible isothermal compression, process 3 to 4, is at constant temperature again, and reversible adiabatic compression processes from 4 to 1 Okay, temperature rises from low to high. So this is called the reversible process. Okay, reversible. All right, so the reversible Carnot cycle, the Carnot heat engine cycle is a totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. Okay, so this is again the Carnot principle. It's saying that in a reversible heat engine, the thermal efficiency is going to be less than the thermal efficiency of the reversible heat engine. And then if you have three heat engines and they're operating with under the condition of two reservoirs, the high reservoirs and the low reservoir, the thermal efficiency of this heat engine and this one, they're exactly the same because they're operating because they're reversible, they're operating under the same condition. But for irreversible process, the thermal efficiency will be less than the thermal efficiency of the reversible. Okay? So the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. The efficiencies of all reversible heat engines operating between the same two reservoirs are the same. Okay? All right, so that's a diagram for that. And this is the high temperature reservoir, and all the reversible heat engines operating between the same two reservoirs have the same efficiency in the second Carnot principle. Okay, so if we have the heat engine, a reversible, another heat engine that's reversible, so the thermal efficiency of A equals thermal efficiency of B. Say we have, if you calculate the thermal efficiency, you can get 70%. All right, so, and then again, the Carnot heat engine, this is the formula for any heat engine is this 1 minus QL over QH, which you have used that on the exam, I think. So, and then for reversible, the Carnot engine, you can, if you have a temperature, so you know the low temperature and the high temperature, you can get the thermal efficiency of a reversible engine. So that's a Carnot heat engine, okay, reversible. So that's a beautiful name of that you always remember that Carnot heat engine it has a reversible process. And again, the same thing here, more diagram. Let's just continue. And then we have a coefficient of performance that they're just the same approach, but again, the thermal efficiency is always less than 1 and coefficient of performance is always greater than 1. Okay. So the Carnot refrigerators and heat pumps, coefficient of performance is 1 divided by QH or QL minus 1. And for heat pump is 1 divided by 1 minus QL over QH. And on chapter 6, there is a derivation on this. Okay. So you can see that on the derivation of this. Carnot refrigerator or heat pumps, that's a formula in terms of temperature. And this in terms of heat. Okay, so the coefficient of performance of reversible refrigerator or heat pump is the maximum theoretical value for the specified temperature limits of the coefficient of performance of a reversible refrigerators or heat pump. Actually, refrigerators or heat pumps may approach these values as their designs are improved, but they can never reach them. The coefficient of performance of both the refrigerators and the heat pumps decreases as the temperature decreases as well. That is, it requires more work to absorb heat from lower temperature media. Okay, so that's the end of it. And I just wanted to quickly to show you this. Let me stop the sharing here and go back to, let me see if I can see the, okay. Can you hear me, guys?
Yes? Yeah, we can hear you.
Okay, thank you. For 1 second, I thought maybe the audio was, or my microphone was turned off. I am trying to share, okay, share this. Let me see here, okay, share that, and that is a very nice one. Okay, all right, so.
What if I told you I built a machine that creates energy? My ingenious design works like this. As the wheel turns, the coins fall in the slots, so that one side of the wheel is always heavier than the other. We should keep wheeling upside down, and the wheel would never stop turning. That's so much the push this wheel would spin forever. Even when the possibilities, I think the winter is that for my all the power never hurt. We don't want your thoughts anymore. Just consider climate change. So let's see the ocean. No, because it doesn't actually hurt. You may have seen this view before, and there's a reason it doesn't work. Well, physics, but also friction here on the outside, which will eventually stop anywhere from continuing to spin. But then there's also gravity. So let me say more about one side of the wheel heavier than the other was misleading, because of the way gravity works on wheels. Imagine what you're doing. Its center of mass is at the center of the wheel. Now imagine a wheel with a single point. Motion machine, a device that is supposed to move without any energy. Conservation of energy, which states that energy can neither be created nor destroyed. Energy never comes for free. If you see a machine producing motion, heat, light, or another form of energy, keep looking for the energy source. I repeat, keep looking for the energy source. So now you know, when you tell somebody about the motion, tell them to put their words elsewhere. Thank you so much for watching.
Okay. All right, that was a good video. Okay. All right, I thought maybe that will excite you about the thermal sciences and perpetual machine. Okay. All right, which is not possible. Okay. right? So any questions? I think that's good enough for time being. I'm going to stop recording.